Christina Williams, who's visiting us virtually from the University of Arizona. Christina earned her PhD from UMass Amherst, where she focused on observations of sub-millimeter galaxies, which at the time were this newly discovered, very mysterious population of galaxies that Christina and her collaborators did a lot of seminal work on with the Aztec camera on the LMT, which was built at UMass. After finishing her PhD, Christina moved on to the University of Arizona, where she was first a postdoctoral research associate and then won an NSF Astronomy and Astrophysics postdoctoral fellowship. And as of last year, Christina is an assistant research professor and astronomer at Arizona. So as we'll hear today, Christina is a leader in observations of galaxies over a broad range of wavelengths using facilities like ALMA and Subaru and the Large Binocular Telescope, which she uses to constrain the dust and gas properties of galaxies, their stellar populations, and the feedback processes that are shaping galaxies and ultimately cause some galaxies to stop forming stars. So she's also heavily involved with the James Webb Space Telescope. She's a member of the NIRCam instrument team and the NIRCam GTO programs, the big programs like JADES, which is an ultra-deep imaging and spectroscopic survey of high redshift galaxies. And she's the PI of 2 Cycle 1 JWST programs, which we'll hear a little bit more about today. So Christina is happy to field questions throughout the talk, so feel free to put those in the chat or raise your hand and I'll ask you to unmute. And so with that, Christina, thanks very much for being here and take it away.
Thank you for having me here. I'm sad that I'm not there in person. I would have loved to visit McGill, and Montreal's a great city. When I was living in Massachusetts, I went up there a few times and I really enjoyed my time there. So hopefully sometime in the future. But today, virtually, I'll be talking about some of the work I've been doing to study massive galaxies in the early universe. And a lot of the stuff that I've been doing is sort of targeting these evolutionary phases of massive galaxies that are kind of challenging with existing telescopes. So that's what the dark side here is referring to, like that it's just hard to get photons to give us information about certain life phases of massive galaxies. And then at the end of the talk, I'll talk about how JWST is going to change that and sort of shed light on these things that we can't really study very easily right now. And JWST is, of course, I'm very excited about that because I've been working as a member of the NIRCam team. And so a large fraction of my postdoc has been dedicated to sort of planning for this really exciting facility. So hopefully by the end of this talk, you'll be as excited as I am. So I will start my talk with a timeline of the universe. So we think that the universe started 13.8 billion years ago with a Big Bang. And after the Big Bang, the universe was filled with hot gas. And this hot gas eventually cooled to collapse and form the first stars that made up the first galaxies. And this early epoch of the universe is basically shielded from our view. So we can't see what happens. Part of the reason is because our current telescopes can't see red enough or faint enough to probe the era when the first stars and galaxies form. So our first view of galaxies starts at about Redshift 11. So that's about 400 million years after the Big Bang. And this is the galaxy the farthest galaxy that Hubble has ever been able to see. And this is sort of at the very bleeding edge of what Hubble can actually do in terms of its wavelength coverage. So if this thing had been a little bit higher redshift, we wouldn't have found it. Or at least been able to spectroscopically confirm it. So this galaxy is whopping bright, which is another reason why we were able to find it. Most galaxies we think are not that bright in the early epoch of the universe. So since Redshift 11, we've been able to sort of take a better census of what the galaxies at each era of the universe look like. And so we sort of have a big picture idea of how galaxies sort of evolve and change over cosmic time to sort of form the diversity of galaxy colors, sizes, and shapes that we see in the local universe today. So this diversity that we see in the local universe today, we've known about the diversity of galaxies for the last century, and it can sort of be summarized by the Hubble sequence classification scheme, which sort of you can see here. And it sort of shows that there's, you can classify galaxies by their shapes and colors, but there's also two broad categories of galaxies that you see in the nearby universe. So there's star-forming galaxies, which tend to have bluer colors because they're actively forming new stars in spiral disks. So this indicates their ages are a little bit younger. There's also what I'm going to call throughout this talk quiescent galaxies, which are galaxies that are not actively forming stars. You can tell that by their red colors. So the red colors are basically saying that the stellar populations are all old. They don't have any new active star formation going on now. And they tend to have these ellipsoidal structures that are still kind of a mysterious thing that we don't totally understand why that goes along with these old non-active stellar populations. So the Hubble tuning fork, there are sort of strong physical parameters that underlie the Hubble sequence. So here I'm showing one of the more famous ones. This is what's known as the galaxy bimodality. So this plot is showing the age of stars in a galaxy versus the stellar mass. So how massive the galaxy is. And these contours are showing galaxies in the nearby universe and how they populate this plot. And so you see that there's a large number of lower mass, younger galaxies, and there's higher mass, older galaxies, but there's kind of a transition where there's not that many. There's fewer galaxies populating this transition era. Above this mass of about 10 to the 11 solar masses, pretty much all galaxies are these sort of red and dead quiescent galaxies. And so this is how I'm going to be referring to massive galaxies throughout this whole talk, are basically galaxies like this that end up sort of red and dead by the time we get to the local universe today. So for reference, the Milky Way is slightly less massive than what we would call massive galaxies in this talk. So from the local universe and looking at the stars and measuring the number of stars of different ages in local galaxies, we can sort of reconstruct a rough star formation history of how we think these galaxies evolved since the Big Bang. So here I'm showing the star formation history that's reconstructed using this stellar archaeology as a function of look back time. So the present day is over here. And galaxies here have been binned up by their mass. So the most massive galaxies are this red one. And so you see here that massive galaxies have this really characteristic star formation history. They start forming stars very early in the universe. They form stars in this extremely rapid and rapid burst of pretty extreme star formation. And then this era of star formation ends rather abruptly, and the whole thing is over by like Redshift 3, which is something like 2 billion years after the Big Bang. So if you go to progressively lower and lower masses, the onset of star formation is a little bit later. The star formation at the level of star formation is less extreme, and then the duration of the star forming era is longer and longer. So we don't really understand what are the processes that determine these different star formation histories with mass. And we really don't understand what sort of drives this very extreme and rapid star formation history of massive galaxies. And so that's basically what I'm going to be talking about today is, what drives these rapid bursts and what drives the rapid truncation of the star formation at very early times. So I'm listing here a few reasons why I think that massive galaxies are interesting and sort of motivate me to continue trying to learn more about them. So first of all, massive galaxies are cosmologically important. So half the stars in the universe formed in the environment of a massive galaxy. So this is, so this is important to understand how these stars are forming. They are, they're massive galaxies. They're the signposts for massive dark matter halos. So an interesting thing about this is that our sort of concordance cosmology lambda CDM predicts that massive halos, dark matter halos, should grow through the hierarchical merging of smaller halos, and so they should become massive later in the universe. But if you look at the baryons of massive galaxies, they seem to grow in the opposite way. So they rapidly grow and build up a lot of stellar mass early in the universe. And so this is, we can use this to sort of better understand how baryons behave inside dark matter halos as galaxies are evolving. So this lets us help trace early universe baryon physics. And like I said, the massive galaxies are forming in a very different way, in a very different mode than sort of typical galaxies in the local universe. So they form 10 to 100 times more stars in about 10% of the time of a typical galaxy today. So this is like a very different mode of growth. And then finally, they represent an opportunity to study sort of what I would say is unknown astrophysics. Like, why do these galaxies stop forming stars? Do they have a supermassive black hole that's truncating the star formation, or do they have, live in a massive dark matter halo that prevents gas accretion? These are all things we don't really understand and we want to better understand. So in reference to this timeline, we think that these massive galaxies are forming very early in the universe. They probably proceed to grow very rapidly in this sort of what you would call the reionization era of the universe, when galaxies are ionizing the intergalactic medium. And we start to see them show up sort of 1.5 billion years after the Big Bang. The first mature dead galaxies show up. And so then by Redshift 1, the majority of massive galaxies are now no longer forming stars. So the workhorse, to study all of these high redshift populations of massive galaxies, the sort of workhorse data sets that we use are deep field surveys. So probably everyone's heard of the Hubble Deep Field. Here I'm showing a picture of the Hubble Ultra Deep Field in the infrared, and there's thousands of galaxies in this picture. And each of these galaxies are at different distances, but we can use their sort of distances and properties to sort of reconstruct how we think as a population galaxies are changing over cosmic time. So, in particular, using Hubble, we've now been able to trace the origin of the Hubble sequence. So, the split between quiescent galaxies that are non-star forming and star forming galaxies back to, about redshift 2, and even a little bit higher redshift than that. And so this has sort of enabled us to study these quiescent galaxies sort of closer to the time that they shut their star formation off in the early universe. So how do we identify massive galaxies from these deep field surveys? Well, just to sort of introduce you to what massive galaxy spectral energy distribution looks like, this is, I'm showing two examples, one a non-star forming quiescent massive galaxy in red, and then a model for a star forming massive galaxy in blue. So this is at redshift 1.5. And so this is the era where there's still sort of massive galaxies of both types. And one thing that is a challenge is trying to determine the difference between these two, because you can see that their SEDs kind of look rather similar in terms of, like, if you were to take just the photometric colors or something, they kind of have a similar red spectrum from the stellar, their stellar populations. So it's really important to try to take measurements across the electromagnetic spectrum to get a full picture of what these different galaxies are doing and determine whether or not they're massive, quiescent, or star forming. So over here on the blue side, this is where the emission is tracing young massive stars that have just formed. The challenge with massive star forming galaxies, of course, is that they have a lot of dust in them, and that dust will redden the UV. And so that makes it really complicated to figure out how many new stars are forming in star forming galaxies. So if you go to sort of the near infrared part, then you can characterize what the older stellar populations are that tell you what this galaxy has been doing in the past in its star formation history. And then importantly, we need some measurement of the long wavelength emission coming from these galaxies. So in the case of the star forming galaxy, this dust that is sort of extinguished the light from the massive young stars gets heated and re-radiates that energy in the far infrared. So that's why this you see this big dust emission bump at the long wavelength end. So this is usually characterized by, for example, Herschel or single dish submillimeter surveys that you can do from the ground. This sort of helps you get a handle on the total amount of new stars that are being formed without having to worry about the dust that is sort of cutting off the emission from the young massive stars. So here I'm showing now just the typical depths of deep field surveys that have been conducted with these different facilities. And so you can see, this is not like the deepest they've ever gone, but it's typical depth. And so you can see that for, redshifts 1.5, we do pretty well at sort of characterizing, we can detect the emission from star forming galaxies and kind of distinguish between these two populations of galaxies. So one thing that's really important measurement that have come out of these deep field surveys is the sort of the galaxy census, like what is the galaxy population, what number of new stars are forming in the galaxy population over cosmic time, sort of on average. So this is a plot showing the cosmic star formation rate density, where the red points are showing the cosmic star formation rate density you would measure from the infrared, where the dust is re-radiating the starlight, compared to what you would get if you just looked at the UV not corrected for dust. So this is just the UV photons that escape the galaxy. And you can see that it's a lot lower because a lot of the galaxies have their star formation obscured by dust. So if you're able to correct for this dust accurately, then you can sort of get a really good picture of what we think the cosmic star formation rate density in the universe was. This is the number of new stars being formed per unit volume across the whole universe. So what we found from that is that early in the universe, like soon after the Big Bang, the galaxies are starting to grow faster and faster, and so the star formation rate density is increasing until about redshift 1 to 3, which is this era of cosmic noon, which it got its name because this is sort of the peak of the cosmic star formation rate density in the universe. So then towards the present day, it starts to decline. We don't totally understand exactly the reason for this. Part of it is that, during this epoch of cosmic noon is when a lot of these massive galaxies stop forming stars, and they're forming stars prolifically early in the universe. So this really decreases the volume density of new stars being formed. I'll also explain a couple of other things that we think may be contributing. So why are massive galaxies stopping star formation very early in the universe? This is an open question. I think it's helpful to think of it of galaxies as like living in an ecosystem where they're being fed from the intergalactic medium with new fuel for star formation. So galaxies in the early universe are constantly accreting new gas from the intergalactic medium that's falling onto the galaxy to fuel star formation, and also the star formation can blow more gas out that can sort of recycle and sort of maintain an active phase for a while. So we've now sort of understood that the overall shape of this cosmic star formation rate density is probably related to the availability of cold gas in galaxies in the universe. And so you can sort of, if you look at the right panel now, you can sort of compare, people have tried to take census of the molecular gas content in galaxies in the universe over cosmic time. And you see the same overall shape, that between redshifts 1 to 3, this is the peak in the molecular gas availability in galaxies. And that's probably why galaxies are forming stars the fastest during this time. So, but that makes molecular gas kind of an important thing to understand why galaxies are not forming stars, because if there's all this prolific gas in the early universe, why are these massive galaxies no longer using that fuel to form stars? So there's a lot of interesting ways you could tackle this problem. I'm just going to share one because I don't have a ton of time to talk about all the interesting things, but I'm just going to pick out one thing that is sort of new result that I think is really an interesting, sheds interesting light on this problem. So quiescent galaxies are hard to they're hard to target because they probably have a low level of molecular gas in them, and also redder stellar populations are fainter. So it's just harder to measure things from quiescent galaxies than it is for star-forming galaxies. But this survey, the Requiem survey, targeted a really unique sample of quiescent galaxies at redshifts greater than 1.5. So this is during this cosmic noon era. These galaxies have been lensed by a foreground galaxy cluster. So that means that the light gets magnified and it gets smeared out across the sky. And so you can study these quiescent galaxies in much greater detail. And I think this is pretty unique sample because I'll just point out quiescent galaxies in general are not a very common population at these early times. They're very rare. Galaxy clusters in the local universe are relatively rare. So this chance alignment is kind of it's a rare occurrence. So it's really exciting that we can identify these quiescent galaxies that have been lensed to study them in greater detail. So we targeted them with ALMA to try to measure their dust continuum. And so the dust continuum tells you that there's a cold interstellar medium, and so you can use this as a proxy to measure the molecular gas. So here's just a zoom in of one of these quiescent galaxies that have been lensed, and the red blob here is dust emission that was detected in one of these quiescent galaxies, which is sort of not expected, but very, very exciting to see that we can measure that. So most of them were not detected. 2 of them were detected, but at very, very low levels of dust and by proxy molecular gas. And so what that's telling us is that these quenched galaxies totally ran out of their fuel for star formation. And so the galaxy shut off its star formation because of that. And that seems like sort of an obvious answer, but at the same time, here on this plot, I'm showing just the fraction of molecular gas as a function of redshift. The sample we targeted are these circles, and the sort of overall star forming population, like the plot that I showed you earlier, showing the molecular gas content as a function of redshift, is up here. So you can see they're well below what is sort of typical for other galaxies of the same era. So it seems like an obvious answer, but at the same time, it's kind of exciting because we didn't really know why the star formation stops. It could be that you just reduce the efficiency of star formation and the gas is still there. So we are able to sort of rule out that idea. So anyway, I can talk more about this later offline if people are interested in some of the ideas that might be either related to supermassive black hole or the mass of the dark matter halo that may be affecting the molecular gas content. So it's, one thing that would be interesting to do is to try to do this for larger populations of quiescent galaxies. And now we're starting to be able to sort of measure and confirm quiescent galaxies that don't form stars up to even like redshifts 3 to 4. So this is one famous galaxy now. It's the sort of redshift record holder of a quiescent galaxy at redshift 3.7. So you can see you can confirm it by these strong Balmer absorption features that are characteristic of older stars and so this galaxy is no longer forming stars and hasn't been for some time, a few 100 million years. This is also sort of at the edge of what's possible, because if you notice the observed wavelength, this is about 2.3 microns. And so if this thing was any higher redshift, we wouldn't be able to confirm its redshift through these Balmer absorption features, or its quiescence through these Balmer absorption features. So JWST is going to help us a lot here, where we can start to go to redder and redder wavelengths. But I think the point is that these things are, we're starting to be able to measure their abundances, these quiescent galaxies, close to their formation epoch. So here I'm showing the number density of quiescent galaxies as a function of redshift. So these new redshift 3 to 4 galaxies are up here in this red point. And so, one thing to point out is that, we thought quiescent galaxies at high redshifts would be relatively rare, but it turns out that they're not that rare. So this is a number density of 3 to 5 times 10 to the minus 5. So that's not a very informative number. But what you maybe want to do is compare it to massive star-forming galaxies around the same time. And it turns out that the massive star-forming galaxies that are, forming stars rapidly enough to evolve into these sort of massive quiescent galaxies on a short time scale, those things are way too rare to explain the emergence of these quiescent galaxies by redshifts 3 to 4. So this is kind of a problem. You can sort of invoke all kinds of arguments like this lifetime of these things needs to be very rapid, but there's a huge discrepancy here. It's like almost a factor of 10 to 100 in abundance. And so that's a problem that that we are facing in sort of taking the census of these massive galaxies sort of above redshift 3, which is when we think they're forming. So, we've identified lots of star-forming galaxies above that redshift, of course, but these are sort of most efficiently selected using their UV emission. And like I said before, the UV emission, to measure that, it has to not be too dust obscured. So we can characterize the significantly dust obscured population. So this is shown here by the luminosity function. So there's bright UV luminous galaxies over here, which are less numerous, and then you have fainter UV luminous or UV faint galaxies over here. So this population is characterized. We understand the UV selected population relatively well, but none of these things are forming stars rapidly enough to form a massive galaxy by redshift 4. These are the things that evolve later. So we have a problem. We're sort of missing this population of star-forming galaxies in the early universe that evolve into these massive quiescent galaxies. So this sort of shows you why we're missing them. This is now a set of galaxy models at redshift 6. So the other one I showed you was at redshift 4, or sorry, 1.5, where we could see that, you know, our current surveys were able to sort of characterize the different parts of the SED. But when you get to redshift 6, all of these things sort of drop below the detection limit of current surveys. And so we have this blind spot where we can't, despite, it's sort of counterintuitive because you think of massive galaxies as being the brightest and easiest to find, but it turns out once you get to a certain redshift, that's no longer true. So sort of counterintuitively, you can much more easily identify low mass galaxies that are less dust obscured because they sort of pop into our optical and Hubble imaging relatively easily. So one way around this is using ALMA. ALMA is a very, very sensitive submillimeter interferometer in Chile, and it can see much fainter and to much higher resolution than single dish submillimeter surveys, which sort of, if you can look over here, this redshift 6 star forming galaxy sort of was dropping to the very edge of the detection limit of these single dish facilities. So ALMA is really exciting because you can sort of better detect these star-forming galaxies, but ALMA is not a survey instrument. You really can't map large areas of the sky very efficiently, so it's hard to search for these things. So one of the ALMA surveys that I had to look at the molecular gas of quiescent galaxies, while we were doing that, we also collected dust continuum, basically far infrared continuum maps. And in one of those maps, so these are 6 quiescent galaxies that we targeted in that survey, one of the maps had these unknown galaxies detected in the continuum. So these are 3 millimeter wavelength continuum. Just for some context here, at the time when we took this survey, there had been a few like deep field campaigns with ALMA to look for things like this, but they were sort of like, you know, on the order of less than 10 square arc minutes. So it's a very tiny field. But when we made this map, it turned out to be about 10 square arc minutes. So it was actually larger than some of the other deep field surveys that had happened. So this was actually a significant amount of new area that we were now adding to the deep field survey in the data archive. So we found these 2 galaxies that like didn't exist in any catalogs. So we took a sort of deeper look to see, you know, what these galaxies were. Turned out the blue one here is just a, you know, it's a redshift 3 dusty galaxy that just happened to be blended with a foreground redshift 1 galaxy. So that wasn't sort of any new insight into the galaxy population at redshift 3. But this one in red turned out to not be detected in any of the existing galaxy catalogs or deep field surveys to date. So here I'm showing the ALMA map that we did. You can see it's very strongly detected. If you look at you know, an optical stack from the ground, there's no emission. Infrared stack from the ground, no emission. Even in Spitzer, which, you know, Spitzer 3 and 4 micron imaging, there's no detection. Scuba 2, which is the 850 micron imager on the JCMT, there's like a barely 3 sigma blob there. And in the VLA 3 gigahertz, there's like a 4 sigma blob. These things help us to, you know, believe that this source is actually a real source. But, you know, the false detection rate at these signal to noise of these maps is like, you know, 65% or more. So you would never believe these things without the ALMA to sort of corroborate that it's a real source. Okay, so it was significantly detected in 1 band with ALMA, but it turned out that because all of the non-detections were so deep that you could still actually pretty accurately constrain its spectral energy distribution. So here I'm showing the flux as a function of wavelength of the galaxy. So all of these little boxes are signal to noise less than 3. And if it was signal to noise less than 1, there's a downward arrow. So here's our ALMA detection here at 3 millimeter. And it turned out that because of the 3 millimeter was so bright and these bands were so deep, you could actually pretty reasonably constrain its redshift to be about 5.5. So this is a pretty high redshift for a dusty star forming galaxy. Some dusty star-forming galaxies have been measured at these early times, but they are like whopping bright in the submillimeter. So, we measured a pretty modest star formation history or star formation rate of like 300 solar masses per year. Most of the things that had been massive dusty star-forming galaxies were like thousands of solar masses per year. So this is kind of a new type of object. You can sort of infer what kind of gas mass this object had, which is it's a lot of gas for a relatively modest star formation rate. And that means that we think that its sort of duty cycle, or the lifetime over which it can sustain this kind of star formation, is actually pretty long. So it's like 500 megayears, as opposed to submillimeter galaxies, which are like 10 megayears. So we think we might be probing a new sort of growth mode of massive galaxies in the early universe. And it would be interesting to sort of better understand this population that's sort of eluded us to date. So if you now take the small area that we found this thing in and you sort of estimate its number density, this is much more in line with what you would measure from the quiescent galaxies. So it might be that these dusty star-forming galaxies that are traced by this infrared dark galaxy we detected with ALMA could sort of explain the emergence of these quiescent galaxies. So one reason this is important is because it's indicating to us that our cosmic star formation rate census is underestimated at these early times. So this is a plot similar to the one I showed you earlier. This is the cosmic star formation rate density, the number of new stars forming per unit volume in the universe, split by those measured with the infrared versus uncorrected by the sort of the UV probed but uncorrected for dust in blue. So given that most of these surveys are using single dish submillimeter surveys, our surveys are relatively incomplete starting around Redshift 5. So this was, a new constraint that we measured the cosmic star formation rate density to be kind of, it's very uncertain. It's only one object, but it could be as high as the uncorrected UV star formation rate constraint. So that's kind of a lot. So we really want to better understand the prevalence of objects like this so we can fill in this gap in our census of the cosmic star formation rate density. So anyway, this is, there's still a lot to be done here. Since this paper came out, a few more examples of sources like this have been discovered, where you have submillimeter emission with no counterpart in any of the other bands. And so I think this is indicating to us that these galaxies are out there, and we need like a wider scale survey to really sort of understand what the numbers are and better understand whether or not this sort of longer growth mode is a thing for massive galaxies in these early times. So there are some more longer wave surveys that are currently going on that will help to fill this gap in. But I'm now going to talk about JWST, which I think is going to be a much more efficient way to sort of search for these massive galaxies in the early universe. So JWST is coming. It's going to hopefully launch in like, I don't know, 32 days. So this is like very exciting. I've been waiting for this for a long time. So here's JWST at NASA while it was getting assembled. And so why is JWST so exciting? Well, it's the largest astronomical mirror that we've ever launched into space, and it also has the most sensitive infrared instruments that we've ever built in space. So just to sort of compare it to existing facilities, I'm showing in this plot the photometric performance of JWST as a function of wavelength compared to other facilities. So this is the signal to noise ratio of 10 achieved in about 3 hours. And so what this is showing you is that in 3 hours of integration time, we're going to go magnitudes deeper than either Hubble or Spitzer was able to do. So also for comparison, I talked a lot about deep field surveys that sort of integrate longer and longer to probe farther and farther into the universe. So these stars are showing kind of the depths achieved by the deepest surveys ever conducted by Spitzer and Hubble. So in less than 3 hours, JWST is going to go deeper than Hubble was ever able to do. And in 3 hours, so this is like the equivalent of 66 hours of integration time per pixel for this Hubble map. And for Spitzer, it's like 200 hours. JWST in less than 3 hours is going to go like multiple magnitudes deeper. So this is really totally new parameter space that we've just never seen what the universe looks like at these faint limits in these wavelength ranges. So in addition to being super sensitive, JWST also has some unique observing modes, and I'm just going to talk about one of them. This is the near infrared camera. This is the instrument that I work most closely on. And one of the interesting things about NearCam is that it's a really efficient imager. It's not just super sensitive, but it can also image in 2 filters at the same time, because it has this dichroic that will split the light and let you make 2 images for basically the exposure time of 1. So this is demonstrated here. There's 2 detectors on NearCam, module A and module B. And then you can see that there's a short wavelength channel that maps the exact same part of the sky as is mapped by this long wavelength channel. So this is really exciting and has enabled some very highly efficient surveys that I'm going to talk about now. So to prepare for JWST, the team that I'm on, which is the Guaranteed Time Observations team for NearCam and NearSpec together, generated this. We built this sort of mock observation tool called Jaguar, which is basically an empirical mock catalog of galaxies across cosmic time that include their photometry, spectra, and other galaxy properties out to Redshift 15. And so it's an empirical model that sort of follows what we know about galaxy scaling relations from deep field surveys like with Hubble. So using Jaguar, we made this image that sort of simulates one of the deepest parts of a deep field survey that we're going to do called JADES. And so here you can see this is zoomed in on several high redshift candidate galaxies from Jaguar, and you can see they have this characteristic red light that we're unable to detect right now, but they're going to pop right out in these JWST images. So this is really exciting. The simulated image is, by the way, 30.3 AV mag, so it's like mind-blowingly deep. All of these images and catalogs are publicly available at this website if you want to explore them yourself. So also just to sort of point out another very exciting feature of JWST, it has a huge diameter mirror, which means the spatial resolution is better. So here I'm showing a simulated field that's made up of Jaguar galaxies, but this has been degraded to that Spitzer survey that I was pointing out before that achieved 200 hours worth of depth with Spitzer. So this is what that Jaguar field looks like with Spitzer. And this is what JWST is going to see. And so it's like the resolution is so much better. You can see all these fainter galaxies. It's just going to be like, I'm just really excited for these surveys to come on. I think it's just going to give us such a clear picture of the early universe that we've never had before. Okay, so now I'm going to talk about some of the surveys that will happen in cycle 1. So here I'm listing. These are approved cycle 1 programs from the general observer selection. And these are all deep field surveys that have, or imaging surveys that have no proprietary period. So they're going to be publicly available immediately upon arrival on Earth. And the exciting thing about this is that if you add up the area that will be available altogether, it's like 1.3 square degrees, which is a huge area because JWST is not really meant for mapping wide areas. So this is really exciting for me because I do a lot of things that require large area science. And I've been thinking, oh, well, JWST doesn't do wide areas. But actually, I think once you add up all of this stuff together, we're going to get some really interesting insight on rare galaxy science in the early universe too. So now I'm going to talk about these two. I'm primarily going to talk about one of the programs that I have approved for cycle 1 called Panoramic. If I don't totally run out of time, I'll also briefly talk about a smaller program that I'm leading that's also has no proprietary period. All right, so Panoramic stands for Parallel Wide Area NearCam Observations to reveal and measure the invisible cosmos. So it's led by myself and Pascal Oesch. And the idea was to map a wide area. So we're mapping 0.4 square degrees to try to find these rare and red galaxies that we can't easily identify now with any of the telescopes we have, and that can only be followed up, like if we want to learn about their physics, they really can only be followed up with 2 to 5 micron spectroscopy. And so that means that they must be followed up with JWST. So JWST has a limited lifetime mission. So it's nominally 5 years. We hope it will last for 10. But that means the early discovery of these rare galaxies is really critical because there's only a few cycles afterwards to follow them up to learn about the physics of these early galaxies. So in order to do this, JWST is not a huge area, efficient, huge area mapper. It uses up a lot of fuel to map wide areas. So we decided to use this thing called pure parallel mode, which I will talk about in a minute, but it's actually very good at minimizing cosmic variance because you can use it to map large uncorrelated parts of the sky. So the way pure parallel works is that the telescope has its focal plane where all of the instruments lie, and they all are pointing at different parts of the sky when the telescope's pointing somewhere. But you can turn more than one instrument on at once. And so the pure parallel mode basically piggybacks on another program that's doing something with one of the other instruments. And we're just going to turn NearCam on while it's doing that and just record data at random locations of the sky. And this means that we don't have to waste any fuel trying to map a large area. We can just sort of take pictures wherever and accumulate a large area of map in that way. So this is kind of a demonstration of how that works. So, the pure parallel will just turn on in these random parts, and then we'll be able to sort of map these they'll be, non-contiguous parts of the sky, but actually that's better because you can do a better job of sort of assessing the abundance of certain types of galaxies that are rare. So here, by comparison, if you make contiguous map, you might point it in the wrong place and have a totally different idea of what the sort of overall number density of things are, because here it's pointed sort of at a void looking area. But with the pure parallel sort of uncorrelated positions, then we can get a better average estimate of how common these galaxies are. So, so this is sort of the survey strategy. An important thing about this is that in the early universe, this sort of simulation in the background is at Redshift 6, but in the early universe, one of the big questions is, how is the universe reionizing? And it might be that rare massive galaxies ionize their environments first and potentially live in these big bubbles of ionized gas. And so if you only map one part of the sky, you might miss those bubbles. And those bubbles are really like an important thing to target for understanding the process of reionization. So we have two primary science goals for Panoramic, geared towards discovering these currently unknown rare and red galaxies. So the first science case is looking for the first star formation at cosmic dawn. So here I'm showing on this left panel, these are the filters we plan to use for Panoramic from 1 to 5 microns. And above Redshift 9, we should be able to very efficiently select galaxies based on this strong Lyman break, which is due to the absorption of the intergalactic medium between us and the galaxy. So in principle, we can detect galaxies up to Redshift 30 if they're bright enough for us to find them. The second science case is to try to complete this galaxy census at Redshift 3 to 7. So looking for these quiescent galaxies and massive quiescent and massive star-forming galaxies in this sort of, in our current blind spot about the abundance of these two different types of galaxies. So this plot is showing some example SEDs for quiescent and star-forming galaxies at Redshifts 4 to 5. And here you can see the depths of our Panoramic, sort of what we call our minimum survey, which we had to define like the minimum amount of integration time that we needed to do our science. So, so we should be able to characterize pretty well these dusty and star-forming and quiescent galaxies at these redshifts. Okay, so just a brief overview of science case number 1, looking for the first star formation at cosmic dawn. We think that Panoramic will be able to detect something like 80 new galaxies at redshifts greater than 9. And we're hoping to get 10 above redshift 12. These sound like very small numbers, but smaller area surveys it seems likely that they will get even smaller number. So so we're trying to go wide so we can collect a larger number of these bright galaxies. And one of the sort of the advantages is that we can look for galaxies like GNZ11, this Redshift 11 galaxy that is expected to be really, really rare. So here's a plot showing the luminosity function. So it's the number density as a function of UV luminosity. Here are a few predictions for the Redshift 11 luminosity function. And GNZ11 is so bright that it's, and it was found in such a small area that its abundance is like 10 to 50 times higher than what is predicted by the luminosity function. So Panoramic will really let us know if this is the case, and if, or it will help us better understand how rare these really intrinsically bright objects are. Another important thing that we want to do by sort of counting and characterizing the UV luminosity of these early star-forming galaxies at redshifts greater than 9 is that it has important implications for how baryons sort of the efficiency with which baryons can form, cause new star formation inside dark matter halos, and basically how efficient the star formation activity is at a given halo mass. So this is the cosmic star formation rate density is a function of redshift. So I showed this plot many times already, but now I'm zooming in on this very early epoch when we, where the measurements are still pretty uncertain. And right now, we've been able to make these measurements out to about redshift 10, but they're sort of scattered and discrepant with each other. And we're not yet at the stage where we can rule out different models. Like, for example, if you were to extrapolate the luminosity function, so the star formation rate density is basically the integral of the UV luminosity function. So, if you were to extrapolate the UV luminosity function measured at lower times, you would end up with this much higher luminosity or star formation rate density at early times compared to what's actually expected from a scenario where the halo, the star formation rate efficiency is constant with varies with halo mass, but is constant with redshift. Sorry, that was a long-winded explanation. I have another slide after this that shows this better. But basically, the point is that models for how these early galaxies evolve vary by a factor of 30, but the best place to sort of get a handle on which models are most consistent is out here at this higher redshift era, where the models diverge enough to distinguish between them. So here is just a little simulation to let you know that I think we are probably going to solve this problem with Jwst. So this is showing the total galaxy counts for the guaranteed time observations survey that I was telling you about. It doesn't really matter that that's the survey that will do it. I'm pretty sure all of the surveys are going to be able to make this constraint. So this is a Jaguar. So when I did the Jaguar simulation, we used this constant efficiency model, which basically means that the star formation efficiency in galaxies is constant with redshift, but varies with halo mass. If you increase the efficiency with redshift, then that means that galaxies are brighter than and therefore more numerous in a survey. And so if we were to observe either of these hypothetical universes, we will be able to tell the difference because you can see that the error bars are small enough to distinguish between these models. So I think we're going to have an answer in the next few years about how early galaxies are growing in their dark matter halos. So the second science case was to complete the galaxy census of redshift 3 to 7. So this is targeting these dusty star-forming galaxies that we really can't easily identify right now. So hopefully we will better understand their contribution to the cosmic star formation rate density by looking for them in Panoramic and better understanding their abundances. And so if the abundances that we measured were right, then we're probably going to get 150 to 200 of them. So just to, I know, with ALMA, it's better with ALMA because you can see that it's a highly obscured by its dust emission. But I'm arguing in this slide that actually I think we're still, even looking with just the infrared data from Jwst, we're still going to be able to identify them enough to do this measurement. So here I'm showing these two circles are showing Jaguar galaxies that have similar brightness to the ALMA only infrared dark galaxy I showed you earlier. So they're like not detected. With JWST, we're going to detect them pretty solidly, and we're going to be able to measure their SED with pretty high fidelity. So these are, the error bars are tiny. And so if you do run a little experiment and try to reconstruct its stellar population model, we're pretty much spot on. And this is in part due to the fact that we use these medium band images that help you, they're a much narrower transmission, so wavelength coverage. And so it's a lot easier to tell if you have these strong emission lines in the band, and it helps you to better construct the redshift. So the other half of this science case too is to look for these massive quiescent galaxies in the early universe, like their formation epoch above redshift 4, where we can't confirm them at all right now. And because we don't know anything about them, models basically are all over the map in terms of predicting what the abundances are. So here I'm showing the number density as a function of redshift of quiescent galaxies, where this shaded region is sort of the range in model predictions, and they're like ranging by a factor of 60 to 100. So you can see here, before cycle 1, the cycle 1 call for proposals happened, we were mapping a tiny area from just the guaranteed time observations and the ERS programs. And so we weren't going to put any constraints on the abundance of quiescent galaxies, it seemed, from sort of our prediction of what we thought we would see. So with Panoramic, and especially with all of the public data combined, we're really going to have a much better idea of how the rate at which these new quiescent galaxies stop forming stars, and we'll be able to identify the candidates to follow them up and try to understand why they stop forming stars. Okay, so I'll just briefly talk about the sort of what our real survey might look like with Panoramic. So Panoramic is going to piggyback on all these other programs, but now that they've approved programs for cycle 1, we have a rough idea of what those parallel slots will look like. So we defined, we said we want at least visits that are 1 hour long, so that we can integrate for at least 1 hour on each of our little pointings. But it turned out that for the real distribution of cycle 1 programs, the distribution of exposure times is much longer. So we're actually going to get much deeper data than we thought we were going to get. So that's what this plot here is showing, is just the number of available visits that we will get, and then how long we think that they're going to go. And most of them are much longer than the 1 hour we defined. So basically what that means is that we're going to sort of construct this sort of ideal wedding cake survey strategy, without even needing to design it. So what this basically means is, so by wedding cake, I mean that we're going to have a range of exposure times, some long and some short. And that is going to help us to, obviously we're going to probe the bright end of the luminosity function where all the rare objects are, but we're also going to be able to have some longer integration times that will let us probe the fainter end too. So here I'm showing the number densities. This is the luminosity function again. This is just a little simulation of what our survey will look like in these red points given our exposure time. So I sort of translated that histogram of visits here to what depth we can reconstruct the luminosity function. So the super short 1 hour slots will be over here, but there are two 23-hour long slots over here, which would basically let us do some things that the GTO teams are doing with their ultra deep pointed survey. We're still going to be able to get some constraints on the faint end of the luminosity function. So this is exciting. Another thing that's exciting is that it turns out with JWST, it's so sensitive that we're basically going to have like a candles quality survey without any ancillary data. So this is a plot showing, it's just a little photometric redshift simulation for our sort of proposed survey, which was to map these images with 6 or 7 filters with NearCam. So this simulation is for 20 minutes per filter. And so we get really good photometric redshift constraints for massive galaxies above redshift or above masses 10 to the 10 solar masses or something. So on the right panel, I'm just comparing the photometric redshift performance to a classical survey like CANDLES that is really amazing photometric redshifts, but we're also going to get almost comparably awesome photometric redshifts from just 6 filters. So so this is going to be a really exciting survey with a range of different ancillary science, not just the ones that we targeted, but I think we're going to end up with like something like 2 million galaxies where we can do lots of other science with. Sorry, that's my dog. Okay, how am I doing on time? Okay, I have 2 more minutes. I'm just going to talk about this real quick. This is my other program, which is it's a small program targeting the Hubble Ultra Deep Field with medium band imaging with NIRCam. The medium band imaging is a really powerful feature of NIRCam. The band passes are much smaller than the broad bands, and that lets you sort of take pictures that at certain redshifts you get emission lines inside the medium band filter, and it lets you sort of image the emission lines very efficiently without needing a spectrum or an IFU. So here I'm showing on the right is the observed wavelength. The medium band filters we're targeting are these orange ones. And you can see how the different spectral features that right now are sort of mostly inaccessible to us, how these spectral features move in and out of the medium bands with Redshift. So we're going to be able to measure and map out H alpha and H beta oxygen 3 and even potentially oxygen 2 out to very high redshifts and sort of better understand the interstellar media of these galaxies. So the goal is to sort of overlay on top of the MUSE what will be public MUSE IFU data that shows you where the Lyman alpha is. And so comparing the Lyman alpha to the H alpha can help you sort of better understand the reasons that how ionizing radiation escapes a galaxy to ionize the intergalactic medium. So this is just a cool little simulation showing how the medium band colors really dramatically change as emission lines go in and out of the filter. So here I'm plotting a bunch of Jaguar galaxies with a range of H alpha equivalent widths. So they're color coded by their H alpha equivalent widths. And you can see the different emission lines going in and out of these filters at different redshifts. So over here, we're probing Passion alpha, Passion beta, H alpha, oxygen 3. So there's a whole range of ancillary science that we can do to sort of better understand how galaxies are evolving using this data. And then this is just one little pretty picture of Jaguar galaxies at different redshifts where this is a color composite of our 3 medium band filters. So you can see depending on which redshift and which emission line, there are different colors in this picture. So I'll just leave you with my summary slide. We don't yet know why massive galaxies stop forming stars. We think it's a process that depletes and destroys cold gas, but with JWST, we're going to find samples to better understand that question. We don't understand what drives the rapid growth, but JWST, we hope, will find us enough samples to target them with ALMA and figure it out. And then there's a lot of public data that will be available in JWST Cycle 1. So I think the next year will be very exciting. So thanks.
All right, thanks, Christina. That was awesome. So we have time for some questions. I see there's one in the chat already from Robert, who is wondering if you could say a little bit more about the assumptions about the dark matter halos that were made in your Jaguar models, maybe the cosmology, HMF. That's
yeah. So okay, so I sort of brushed over some details. We didn't actually assume a model for the dark matter halo evolution. What we did was tie our model directly to the observed UV luminosity function. So, so what we actually did was just we chose. Where's that slide? Okay, so we chose to pin to this these Redshift 10 UV luminosity functions that had been measured that seem to follow the sort of what had been referred to as this accelerated decline in the number counts, but it actually was in line. Well, I guess maybe Jordan will have many caveats to this statement, but it sort of followed the expectation that if the halo efficiency does not evolve with Redshift, then you expect this decline in the number counts that accelerates beyond redshift 8. So I mean, all we did was basically pin, we made a decision about which UV luminosity function to pin to, and we just did that. Hopefully that answers your question.
Thanks. Okay, so we have a number of hands up, which I'll go to next. Mohit, do you want to unmute yourself?
Sure. Nice talk, Christina. So my question is regarding the unusually large number of massive quiescent galaxies you have detected at high redshifts. I'm just wondering how much this observation or unusualness of this observation depends on the assumed initial mass function.
I actually, I think, so the abundance itself probably doesn't, but I think you're like pointing out an important point, which is that, so let me answer your actual question first, which is that I don't know if they really depend on the initial mass function that much, because the initial mass function would change the mass measurement, but it wouldn't really change the number that you identify unless your selection effects are affected by your choice of the initial mass function. So there may be a small range of star, like specific star formation rate, where that may matter, but I think what matters more is your decision about how you identify a quiescent galaxy. And so actually, this is sort of exactly the point. This way. This is exactly the point, which is, I mean, this plot only shows a few surveys, but there have now been a few more surveys that find a pretty discrepant number in the abundance here. Actually, the better plot to show is, sorry, this one. All of these surveys, these are observed surveys that are the black points. They all have different selections and different input data sets. And as you can see, these choices result in a hugely varying abundance measurement. So part of this is that our data is sort of not ideal at these very early redshifts for sort of identifying things like that. But I think this, this is an important point, that how you wish to characterize a quiescent galaxy matters at this early time, where there's a lot of like things are recently stopped forming stars. And so, so yeah, hopefully that answered your question.
Okay, next question, Tracy, do you want to go ahead and unmute?
Sure, so that was a really inspiring talk, Christina. I really enjoyed it. And I'm looking forward to chatting with you tomorrow as well. I have sort of kind of two vague questions that are probably related to each other. And I really just wondered if you could say a little bit more about clustering and merging. And so I'm interested to hear your thoughts on, so you talked a lot about how we trace the number density of these galaxies, and you're looking for star-forming galaxies at high redshift that have the right number density to grow into these galaxies at, say, redshift 3. But if you start to throw in some merging, as we know there must be some merging happening, that will screw up your number density. Yeah. And also, related to that, I think these massive galaxies at high redshift are, of course, going to be clustered, which you're trying to get around by your very ingenious strategy of sampling many different fields. But many of us would actually like to find the clustered objects so that we can study large numbers of these things. So if you can talk a little bit about the problems of clustering, but also the signposts maybe that we want to use in order to find these things more efficiently.
Okay, so first question about the sort of, how merging might be affecting these number density estimates. So merging is hard to measure. As far as I know, I mean, the number of objects that fall into this blue point right here is really small. From what I know of them, almost all of them have evidence that they're a major like train wreck merger happening. So they're like there are multiple components, they're disturbed, they're like, a lot of them are targeted with ALMA, and they have, you know, velocity components that you can directly tie to being, you know, an active merger. So that obviously sort of complicates things a little bit, because I mean, these are all potentially mergers. The thing that we found, we actually don't know what it is, but there's no, you know, it's all unresolved in the data we have. So, you know, it's possible that this could merge with other things, and that would, you know, a factor of 2 change in the number of these things that they're merging with each other could impact the outcome of the abundance. So I don't know, this isn't the most eloquent answer to your question. I guess my answer is I don't really know. I don't really know. There is evidence that this population is merging, but I guess to further complicate the answer, this thing that we found, or I didn't, sorry, this is not my work, but this galaxy was later discovered to have a very close companion that's actually a dusty star-forming galaxy. So it could be that in the future, this thing is no longer a quiescent galaxy because it rejuvenates with this actively dusty star-forming thing. So there's uncertainty in the number density of the quiescent side as well. So, so yeah, it's a complicated thing, I think. You're right. So about the clustering, to be honest, I haven't given much thought about that. I mean, one of the things that we sort of wanted to make sure we could do was like measure the abundances with small enough error bars to rule out some of these models. But in theory, we hope we'll find some of these sort of super biased regions that would be the sites of overdensities. I don't actually have a good idea how likely that is. It might be that we have to wait for W first for identifying like really overdense sort of like super protoclusters, I guess, is like the super early protoclusters. But the fact that we're getting wide area, I guess, is a good thing in terms of public data. Maybe there's going to be a way to look for significant overdensities with that data.
Okay, and last question, Adrian Liu.
Hi, thank you very much for a really, really fun talk. I am very excited for JWST.
Yeah.
And could you go back to your the SED for the your ALMA galaxy?
Yeah.
Yeah. So I'm a complete outsider when it comes to these sorts of fits, but I was just wondering that that point, that second last point on the right, like
this one?
No, like further, that those 2 blue points out here.
Oh, sorry, I had the
yeah.
Zoom was covering them. Yeah. So these are
yeah. Do I need to worry about that last point, or is that that seems a very highly significant discrepancy? Yeah.
Yeah, so I totally brushed over this. So this point is a non-detection. The detection limit of that survey is too high. But this one, this is the 4 sigma detection in the VLA. So basically what this means, this extrapolation here with the dashed line is sort of, if you were to integrate the total infrared luminosity, there's a correlation between the total infrared luminosity and the radio emission. It's not super well known whether or not that relationship evolves with redshift significantly, although like recent surveys suggest that it does not. So we put that on there. It's in excess of about 3 times. I think that there's 2 possible explanations for that. One is that this galaxy is actually at slightly lower redshift. If the galaxy is at slightly lower redshift, this thing goes down, this moves this way, and then you can sort of bring these into agreement with each other. But there's a lot of scatter in that relationship, so that's not for sure the only explanation. The other possible explanation is this thing has an AGN of some kind that's boosting the radio emission. Of course, we don't have any other way to corroborate whether or not that's the case. So I tried to get a spectrum, because if we got a spectrum of this, then you would know exactly whether or not it has an AGN or it has a radio excess, but no ALMA TAC to date has agreed to approve it. So
Okay, thank you very much.
Okay, we should probably wrap it up there. But thank you again, Christina, for coming to visit us. That was an excellent
Yeah,
talk.
thanks for
And,
having me.
I welcome everyone else to join me in leaving a note for Christina on your way out, or